There's a part of our operating system that many of us think we know very well, but in reality, we often completely overlook. We take it for granted. I'm talking about the Linux kernel. Linux is Linux, right? Well, in this video, we're going on a journey into the project and its evolution, and I guarantee that after watching it, when you hear someone mention the Linux kernel, you'll have a much clearer and more accurate idea of what it actually is. It has no graphical interface, no icons, no transitions, but this isn't just a story about code. It's a story of revolution. A story that starts with a university student and reaches all the way into the boardrooms of the world's largest tech companies. A story that begins with an email, and that, truthfully, still isn't over. Today I'm going to tell you the real story of the Linux kernel, how it was born, how it evolved, how it works today, and why it's one of the most incredible projects in the history of computing. With one key milestone, the creation of the Linux Foundation. It's 1991. Linus Torvalds is a computer science student at the University of Helsinki. He loves programming, he hates closed-source operating systems, and he's playing around with Minix, a Unix-like system used for educational purposes. But Minix has too many limitations. So he decides to write his own kernel, from scratch, to learn for fun. On August 25, 1991, he posts to the comp.os.minix newsgroup, "I'm doing a free operating system, just a hobby, won't be big and professional like new." That message starts a tidal wave. Many reply, some enthusiastic, others skeptical. But one thing is clear, the code runs. The kernel starts to take shape, and in 1992, Linus releases version 0.12 under the GPL license. Anyone can use it, modify it, share it. It's the beginning of a revolution. But not everyone is impressed. In January 1992, Andrew Tannenbaum, the respected professor who created Minix, fires a shot across the bow. In a post titled "Linux is Obsolete," he attacks Linus's design choices. Linux uses a monolithic kernel, he argues. All drivers and system services crammed into one massive program running in kernel space. It's a relic of the 1970s, he says. Modern systems use microkernels, small modular designs where services run in separate processes, more stable, more elegant, more future-proof. Don't get me wrong, I am not unhappy with Linux, Tannenbaum writes, but then delivers the crushing blow. As a teaching tool, it is excellent, but as a modern operating system, it is obsolete. Linus fires back. Sure, microkernels are theoretically beautiful, he admits, but they're slow. Message passing between processes creates overhead that monolithic kernels avoid. The fact is that Linux is here and new isn't, he writes. Practicality trumps theory. The debate rages across newsgroups, academic purity versus real-world performance, the established professor versus the upstart student. Years later, the irony becomes clear. While Tannenbaum's Minix remains an educational curiosity, Linux powers everything from smartphones to supercomputers. The kernel is the bridge between hardware and software. When a program wants to read a file, write to disk, send data over a network, or show something on screen, it doesn't do it directly. It asks the kernel. The kernel manages memory, processes, devices, and file systems. It decides who gets access to what, when, and for how long. It's invisible, but it's everywhere. And even though the word Linux is often used to refer to the whole operating system, Linux is just the kernel. Distributions are Linux plus everything else, new tools, desktop environments, software packages, and so on. The Linux kernel isn't controlled by a company. It's not a closed project, nor is it chaotic. It's a hierarchical but collaborative system. At the top, there's still Linus Torvalds, who acts as the final reviewer and project lead, but there are hundreds of maintainers responsible for specific subsystems, drivers, architectures, file systems, the scheduler, networking. Everything happens via mailing lists. The Linux kernel doesn't use GitHub, GitLab, or any visual interface to discuss code. Even today, it's all done by email, through the historic LKML, the Linux kernel mailing list. Patches are submitted as plain text emails, containing a detailed description of the change, technical justification, benchmarks if needed, and a signed-off byline for legal and transparency reasons. Approved code flows upward, from contributors to maintainers of each subsystem, then to lieutenants who manage broader sections, and finally to Linus Torvalds, who has the final say and merges code into the mainline kernel. Linus only accepts patches from his trusted lieutenants. This is the pull-based model. Linus pulls changes from trusted repositories. Every 9 to 10 weeks, a new stable kernel version is released. There's a 2-week merge window for new features, followed by a release candidate phase, where patches are tested and polished. Beyond Linus Torvalds, there are other key figures who deserve recognition, developers who represent the human engine behind Linux. Greg Crowe-Hartman, who maintains all stable and long-term kernel releases. Andrew Morton, in charge of memory management. David Miller, longtime networking maintainer. Ingo Molnar, expert on the scheduler and real-time systems. Al Viro, responsible for the virtual file system. Theodore Tso, maintainer of the XT4 file system. Thomas Gleichner, who leads real-time Linux efforts. And Chris Mason, creator of the BTRFS file system. At first, Linux was a toy for hackers. Then it became a tool for students. Then a server operating system. And finally, it entered the enterprise world. That's when the need for coordination became obvious. In 2000, OSDL, the Open Source Development Labs, was created to support collaborative Linux development in the business world. Among its members was Linus Torvalds himself, who left his job to work on the kernel full-time. In 2007, OSDL merged with the Free Standards Group, giving birth to the Linux Foundation. The Free Standards Group was a consortium created in the late 90s to standardize the Linux ecosystem, which at the time was extremely fragmented. It was made up of companies like IBM, Intel, HP, and Red Hat. Its main achievement was the definition of the Linux Standard Base, or LSB. The LSB defined technical standards like the File System Hierarchy Standard, a set of core libraries like glibc, libm, and libpthread, a common set of essential shell commands, the ELF binary format, and a stable ABI. Linux itself never formally adopted the LSB, but it was indirectly shaped by it. When the Free Standards Group merged with OSDL, the Linux Foundation inherited both the technical development side and the mission of promoting standardization. Today, the Linux Foundation is one of the most powerful and influential institutions in modern computing. In 2023, it managed a budget of over $260 million, with 45% of its revenue coming from corporate memberships and sponsorships. Yet, only 2% of that budget went directly to kernel development. The rest went toward cloud computing, artificial intelligence, training, and certification. Rather than listing the thousands of companies that contribute to the Linux project, let's focus on the big names that don't. And none is more notorious than NVIDIA. NVIDIA's relationship with Linux represents one of the most famous conflicts in computing history. Despite building an empire worth hundreds of billions on the back of Linux, from data centers to supercomputers to AI training farms, NVIDIA has historically contributed almost nothing to the kernel itself. The tension reached its peak in 2012 when Linus Torvalds, Linux's creator, delivered his infamous verdict at a conference in Finland. When asked about NVIDIA's support for Linux, Torvalds didn't mince words. He gave NVIDIA the middle finger and declared, "NVIDIA, fuck you." The moment went viral, crystallizing years of frustration from the Linux community. But why such animosity? The issue runs deeper than simple corporate selfishness. NVIDIA has maintained a strict, closed-source policy for their graphics drivers, the critical software that allows Linux to communicate with NVIDIA hardware. While they provide these proprietary drivers, they've refused to open-source them or contribute meaningfully to the open-source Nouveau driver project that attempts to reverse-engineer NVIDIA functionality. This creates a fundamental philosophical conflict. Linux thrives on transparency, collaboration, and shared code. NVIDIA's approach, taking freely from the open-source ecosystem while giving little back, violates the community's core principles. It's particularly galling because NVIDIA's success in AI and high-performance computing is built entirely on Linux infrastructure that others freely contributed. The irony is profound. NVIDIA GPUs power the vast majority of Linux-based AI training, cryptocurrency mining, and scientific computing workloads. Every major cloud provider uses NVIDIA hardware running on Linux. Yet NVIDIA treats Linux developers as an afterthought, providing minimal documentation and keeping their driver code locked away. Recent years have shown some movement. NVIDIA has begun open-sourcing some components and improving their Linux support, but the damage to their reputation in the Linux community runs deep. The NVIDIA fuck you moment has become legendary not just for its shock value, but because it crystallized the frustration of an entire community that felt exploited by a company that profited enormously from their work. NVIDIA is not left alone in this dirty game. Apple, unsurprisingly, given its closed ecosystem, has never shown real interest in contributing to Linux kernel development. Their focus remains entirely on their own operating systems. And Amazon, which builds the entire AWS infrastructure on Linux and generates tens of billions in revenue from Linux-based services, contributes remarkably little to the kernel's actual development. Like NVIDIA, they're happy to profit from the work of others while contributing minimal resources back to the project that enables their success. The very first version, Linux 0.01, had just 10,000 lines of code. A month later, version 0.02 could run Bash and GCC. It was written in C language and assembly for 386 processors, with the goal of creating a free alternative to Minix. In March 1992, Linux 0.95 introduced support for X Window System. Suddenly, Linux had a graphical interface. In May of the same year, version 0.96 implemented virtual memory. Then came the 0.99 series, the almost 1.0, releases that lasted nearly 2 years. Finally, on March 14, 1994, Linux 1.0 was born. This was the moment Linux went from experimental to enterprise-ready. The revolutionary features of Linux 1.0 included the TCP/IP networking stack, which allowed Linux to connect natively to the internet. There was virtual memory management for serious applications, POSIX compliance for Unix compatibility, and support for loadable modules without rebooting. The code had grown to 176,250 lines, a massive leap from the original 10,000. The impact was immediate. Major companies started taking notice. This wasn't just a student project anymore. On June 9, 1996, Linux 2.0 arrived, the version that made Linux truly scalable. The game-changing feature was symmetric multiprocessing, or SMP. Linux could finally use multiple CPUs efficiently. Other innovations included improved networking with IPv6 foundations, kernel modules for dynamic loading and unloading of drivers, memory management overhaul for better performance on larger systems, and support for multiple architectures like Alpha, Spark, and PowerPC. The code had grown to 777,956 lines, nearly 5 times the growth from version 1.0. This version powered early web servers during the dot-com boom. Companies like Yahoo and Amazon started building their infrastructure on Linux. Linux 2.2 in 1999 brought better SMP scaling and new file systems. Linux 2.4 in 2001 introduced USB support, Bluetooth, and enterprise features like LVM. On December 17, 2003, Linux 2.6 arrived, the release that changed everything again. This wasn't just an update, it was a complete reimagining of what an operating system kernel could do. Revolutionary architecture changes included a new scheduler called O of 1, which guaranteed constant time task scheduling regardless of system load. The preemptible kernel gave real-time responsiveness for desktop users. The native POSIX threading library, or NPTL, brought a massive threading performance boost. For audio, there was a revolution with ALSA, Advanced Linux Sound Architecture, which provided professional-grade audio support, replacing the old OSS system. Hardware management improved with UDEV for dynamic device management, eliminating static dev directories. Native SATA support arrived for the new storage standard. Improved ACPI brought better power management and hardware detection. Security became a fortress with SE Linux integration, mandatory access controls developed by the NSA. The capabilities system allowed fine-grained privilege control. The Crypto API provided a built-in cryptographic framework. Virtualization foundations began with early KVM development, Xen hypervisor support, and container primitives with namespaces and control groups, or C groups. Performance innovations included ZSwap, compressed swap cache for better memory utilization, ZRAM, compressed RAM block device, and huge pages support for better memory management for large applications. The code had grown to over 5,900,000 lines by version 2.6.39. In 2011, Linus Torvalds made a controversial decision, jump from version 2.6.39 directly to 3.0. Not because of massive changes, but because 20 years of Linux deserved recognition. The Linux 3.x series brought better power management that dramatically improved laptop battery life. There was a graphics renaissance with better GPU drivers and KMS kernel mode setting. The container explosion made C groups and namespaces mainstream thanks to Docker's rise. The ARM revolution made Linux the backbone of the smartphone era. On April 12, 2015, Linux 4.0 arrived, the version that never needed to reboot. The live patching revolution with Kpatch and Kgraft allowed applying critical security patches without rebooting. The impact was that data centers could maintain 100% uptime even during security updates. Virtualization mastery improved with KVM improvements for better performance isolation, VFIO for direct hardware access for virtual machines, and nested virtualization for VMs running inside VMs efficiently. The BPF revolution came with Extended Berkeley Packet Filter, or eBPF, which allowed programmable kernel without kernel modules. Applications included network monitoring, security, and performance analysis. Companies like Facebook and Netflix built entire monitoring infrastructures on eBPF. For storage and input-output, I/O Uring was a revolutionary asynchronous I/O interface. Applications like databases saw 2 to 3 times performance improvements. Native NVMe support arrived for modern SSDs. Innovation continued with Control Groups version 2 for better resource management for containers, BPF JIT compiler for even faster programmable networking, KSLR or kernel address space layout randomization for security, and KASAN, kernel address sanitizer for catching bugs. On March 3, 2019, Linux 5.0 arrived, the kernel ready for the next computing revolution. The file system revolution brought native exFAT support for Microsoft's extended FAT, F2FS improvements for flash storage optimization, and BTRFS maturation with advanced file system features becoming stable. Networking evolution included WireGuard VPN, a modern secure VPN built into the kernel, simpler than OpenVPN and faster than IPsec, adopted by major VPN providers within months. Security hardening brought kernel lockdown to prevent root from modifying the running kernel, LSM stacking for multiple security modules working together, and hardware security with Intel CT and ARM pointer authentication. Architecture expansion included RISC-V support for the open-source CPU architecture. The significance was that Linux was ready before RISC-V hardware even shipped. Linux 6.x from 2022 to present represents the AI and sustainability era. AI and ML acceleration improved with better support for NVIDIA, AMD, and Intel AI accelerators, memory management optimizations for large ML model training, scheduler improvements for better handling of AI workloads, and NUMA awareness for optimized memory access for multi-socket AI servers. The hybrid CPU revolution brought Intel P-Core E-Core scheduling for optimal task placement on hybrid architectures, AMD ePUC improvements for better support for high core count processors, and ARM Big Little for efficient scheduling for mobile and edge devices. Energy efficiency focus included better power governors for smarter CPU frequency scaling, suspend resume improvements for faster wake times and lower power consumption, and thermal management for better handling of overheating scenarios. Sustainable computing brought code sustainability by removing legacy code and improving maintainability, Rust integration for memory-safe systems programming language support, and developer experience with better tooling, documentation, and debugging. The evolution of lines of code tells everything. In 1994, version 1.0 had 176,250 lines. In 1996, version 2.0 had 777,956 lines. In 2003, version 2.6.0 had 5,929,913 lines. In 2019, version 5.0 had approximately 26 million lines. In 2024, version 6.8 has over 30 million lines. The contributor growth is equally impressive. In 1991, one contributor, Linus. In 1995, about 100 contributors. In 2005, about 1,000 contributors. In 2024, over 25,000 contributors, from over 1,500 companies. Market dominance speaks for itself. 100% of the top 500 supercomputers run Linux, 96.3% of cloud servers, 71% of mobile devices through Android, 62% of embedded systems. Linux pioneered the distributed development model that now dominates software. Git version control was created by Linus specifically for Linux development. Continuous integration brought daily releases and constant testing. Meritocracy means code quality matters more than corporate politics. The open source ecosystem sparked thousands of other projects. Industry transformation includes cloud computing with AWS, Google Cloud, and Azure, all built on Linux. Containerization with Docker and Kubernetes ecosystem. DevOps revolution with infrastructure as code and automated deployments. Edge computing with IoT devices, smart cars, and industrial systems. Today, as you listen to this, Linux is probably running on multiple devices around you. Your Android phone, your smart TV, your router, maybe even your car. The hobby project that wasn't going to be big and professional now powers the internet, enables cloud computing, and makes modern life possible. But the story isn't over. With AI workloads, quantum computing on the horizon, and new challenges in sustainability and security, Linux continues to evolve. Every 9 to 11 weeks, a new kernel version is released, each one pushing the boundaries of what's possible. The Linux kernel isn't just software. It's proof that collaboration, innovation, and the free exchange of ideas can change the world. And the best part? The next chapter is being written right now.